So my dear students, when we come across to the second simulation or the second experiment, this experiment is based on integration frequency selection amplifier. Here for reference I have took op-amp integrator circuits. So there are a lot of circuits that you can elaborate it up to, but you have to go through to there. There is a section right now, the section that do the frequency integration. Which section is responsible for frequency integration? That is the op-amp active filter section. Just like this section is currently using as an integrator part. So we have to just construct it with our own values to understand and measure the things. Not take too many hassle of it, just to study and observe these things. So here we should take the input voltage as 100 millivolt, and the frequency should be 4.5 megahertz. And for this, first of all, we have to again carry out the same calculation, that is F equal to, here R and C is in the circuitry, so twice by RC will be the key factor or important factor in that part. So there are R2 and C1, there should have to be R2 and C1 part. So we have taken 4.5 megahertz and 100 millivolt. So for 4.5 megahertz, just put 4.5 megahertz and the value of any kind of value. I have taken R2 as constant, that's 10 kilo ohm, and I have taken the C1 from the calculation by it. So after calculation we get 3.53 picofarad. Then the simulation comes through. After simulating, it's a very simple integrated circuit. You can draw at your own. Go through to this part, that is the grapher section. Now I go through to the grapher section very much clearly. What does integration do? If it is sinusoidal signal, that will go through to the cosinusoidal signal, that's all. But not it will not be different for that. So in this experiment, what they want from us, that is the frequency meter. The changing the frequency, we have to just draw the output and input frequencies. Okay, how can we do this? So here is the thing, that is the source in 10 kilo range position. That means we have to take the positions 10 kilo range in each portion to a certain value to make up this thing. So first of all, we have to make a table to find out this frequency versus output sections. Okay, to put the value of the output sections too. So just get onto the factor, that is here the output peak to peak is just like it is the top of the point is around 561.38 millivolt, and that is minus 561.38 millivolt. So that is quite a simple sinusoidal circuitry. Now getting onto the schematic portion, you can also take the value from here, but that should have to be peak to peak value. So in case of that, we have taken 4.5 megahertz as a reference frequency. So as a reference frequency, that is FR or resonance frequency, that means that is center frequency. So we have to take, if we want to really just draw the output versus frequency curve, we have to take some other things too. That's a 10 kilohertz potentiometer or 10 kilohertz frequency knob to change the value from 4.5 to that. So what that should make sense, that should have to be changed between some bandwidth. Okay, how can we make to understand this? First of all, go to the grapher section, and there are some selective measures, that is interactive transition. What is the transient section? After simulating, the transient part is like that. That is the transient part. Just stop this and go through to the AC sweep. What does AC sweep? Just simulate this, you will get the AC sweep. There is the AC sweep part. There you can also understand the frequency range change and all other things. And that is here you can understand, and here you can find out the cutoff frequency too. So here you can see there is a minus 3 dB decimal logarithmic change. How that can you find it from here? Just go through to there. You can get onto the first what can I say, auto fit magnitude. Okay, I have just fit the magnitude, and there are some values that is on the logarithmic part, so make it onto the decibel range. So now you can understand clearly what is minus 3 decibel. Go through to the cursor and go through to here, that is 16 and 14 decibel, all other things are there. Just where is the minus 3 decibel, you have to find out that. That is the point. It's a millidecibel or 3 decibel point. Just find out the card, or minus 3 decibel, whatever else it might be. Here is the portion, in that middle of that 4.22, just the point like that, just 39.811 megahertz part. That means quite similarly, that if it is equal to 4.5 megahertz or all, that it will get through to the minus 3 dB in that part. So again, go to the interactive part, simulate the same circuitry here, and yes, I have to pause it. Okay, right now that is the total circuitry and the other parts and parcels of it. So we have taken 3.53 picofarad of capacitor to find it out. So after getting the simulation results, how can we plot it? Let us discuss. For this graph, I have to make a table right through from it to find out this. So I will study for 4.2, 3, 4, 5, 6, 7 and 8, and take the output value out of it. So let us start first. Okay, first of all, we have to take from 4.2 megahertz. Okay, the same voltage 100 millivolt will go through to it, input voltage. Okay, let us start from the grapher. We will go through to the grapher section. Okay, that's the grapher section. Now the topmost is 502, the last is the 589 millivolt, and 589 into 2. Okay, 589 into 2, that will be 1178 millivolts. So now we will find out the other values, then we will try to do the graph. After the total inspection, now the file has been filled. Total, that is the data that I have acquisition. I have taken the data from the circuitry. Now that is the final data that you can see here. Now we should plot it. If you plot it, you will get the value out of it, that how that will look like. Just plot it on a sketch. It will sketch if you have to sketch here. Okay, so that is your output data. So thanks for being with me. That's all for now.